today. So first up, I think Jason probably doesn't need very much introduction. We probably all know him and interact with him on a regular basis with our projects and other things. But if you don't know, he's been on an interesting journey from rocket scientist in America to building scientist here in New Zealand. So welcome, Jason.
All right, thanks everyone. Can you hear me on the speakers back there? All right, sweet, that's good. All right, this presentation is going to be a bit challenging for me because I get terribly excited and speak really quickly. That doesn't work very well for anyone but me. So let's try not to do that. Elron has already introduced me in a bit about us, but I run a small consulting firm with about 6 staff, and we do a lot of energy modeling across the country. We're very, very privileged, and then we get involved in a lot of projects in a very small way. So we have a kind of a good perspective across those projects. And today we're going to talk about fRSI, which is the minimum temperature indicator. But before we get into the technical content, I kind of want to give you a bit of background. So my first home in New Zealand was actually quite a warm house with a very nice gas-fired heater in it. And we got freaked out on the first winter when there was black mold in the bathroom out in the back of the house, because that's not something you accept in America. So when we actually, canceled our lease, which our landlord was grumpy about, and moved to another house, which had even more mold, but that's another story. So the mold in that house, I would say, is not my fault. I was heating to 22 degrees all the time. Like I just left the heater on and ventilated well because the house was quite drafty. It was an old batch. And, I argued that the mold in that house was not my fault. It was just a function of the way the building was built. And unfortunately, that's pretty true across the country. So when people ask me for advice on buildings and they want to avoid mold in their homes, or they want a healthy home, I say you need to both ventilate and heat. And the reason that that's so important is what you're controlling by ventilating and heating is the relative humidity inside the building. Now, the reason you can control the RH, the relative humidity inside the building, and generally bring it down is because you're bringing in outside air that was colder than the air inside the house. So when you bring a quantity of air from outside, it's whatever humidity it's at, and you bring it inside to heat it up, it has the ability to dry out the house, which is why you use a blow dryer in the hot setting to dry your hair, not the cold setting. It does much better because it's got the ability to dry the air out. Because when you raise a quantity of air that's got a certain amount of moisture in it to a higher temperature, the relative humidity drops and allows it to dry. Right? Because we can control the amount of air. That's why we heat and ventilate. Now, if you have that quantity of air again in the center of the room at some temperature and humidity, let's pretend it's at 20 degrees centigrade and 50% relative humidity, which is quite a comfortable condition for people. When you take that quantity of air and you move it to a surface on something, in this case, I've drawn a corner of a building with no insulation in the corner between the studs in there. And as you bring that little pocket of air to the surface is colder, right? And which means that on that surface, the temperature in this case is just under 12 degrees centigrade. So the relative humidity on that surface is 83% relative humidity. That's what that house at really good conditions, right? It's been heated to 20 degrees centigrade. It's been ventilated well, so it's 50% RH. But on that surface, it's 83% RH. Now, why does that matter? It matters because when you look at mold growth on a surface, it's a function of effectively 4 things. It's a function of the temperature on the surface. It's a function of the moisture level on the surface. It's a function of material of the surface again, and time, all right? This, of course, assumes that it's a real environment with dust. It's not a spaceship, right? And so this graph, which I've drawn by hand to make it obvious that it's not ideal, it says basically if you look at the horizontal line at 80%, the relative humidity is on the vertical axis. There's probably a laser thing on here. Yeah, you can see this line here. So basically, it doesn't work very well. So the basically, if you stay below 80% RH on the surface, then you don't get mold at any temperature all the way across this x-axis, right? So otherwise, you've got to be at quite cold temperatures on the surface if you want to have higher RH. And it's a function of material, but if you just stay below 80% RH on the surface, then for any material, pretty much you don't get mold growth, right? And that is the criteria we try to use in Passive House because it's easy and it generally covers things. So when we talk about fRSI, fRSI is a calculation we do. We do a thermal model of the building envelope. And that model applies anywhere in the world because we just put a temperature inside and outside and look at the ratio across there. So this equation says you take basically you do this calculation in a complex software like Flixo or Therm, and then you take the coldest temperature on the inside surface and subtract the external temperature over the internal air temperature minus the external temperature. You get this ratio between 1 and 0. And the point being is that you can calculate this ratio once for construction. I'm not using it anywhere in the world, right? It's not a function of anything else, but it only tells you the temperature on the surface for a delta. It doesn't tell you about all the other things about mold. So the guidance we used to have was to take this ratio and use a map like this. And this map, which is no longer valid, by the way, was what we had up until Pass-Files Planning Package 10. And what it says is that effectively you want an fRSI above 0.55 to avoid mold in those things that are colored kind of yellow or gold. And you want to be above 0.65 in the ones that are green and above 0.7 in the ones that are blue. In other words, as you got colder in the country, you needed to have a better thermal envelope, a better quality of construction, right? A higher interior surface temperature. And that made sense. And that was based upon a lot of experience from Europe, primarily in Northern Europe. And this is true for Northern Europe. As you get colder, you need to have a better and better fRSI to avoid moisture problems, mold on the interior surface. Turns out this is not applicable for New Zealand. It's not a good idea. Right? So, oops. So sorry about that. When Pass-Files Planning Package 10 came out, this is from the front verification sheet for Pass-Files Planning Package 10. And please do warn me on time if you give me 2 minutes. Thank you. This is the sheet, and I've kind of blurred out all the figures so you don't get distracted. But effectively, when you can unlock the sheet and then push the plus over here, which makes the sheet a bit bigger, and it shows this moisture protection section of the sheet. And on the moisture protection section of the sheet, you have this number here, this 0.57. That's the fRSI requirement. So what's going on inside Pass-Files Planning Package 10, it's doing a moisture balance where it's taking the ventilation rate and the moisture generation inside and the temperature and figuring out when it's 80% RH on the surface, right? And so if you had an fRSI of 0.57, the moisture, the RH on a surface with an fRSI of 0.57 in this climate would be exactly at 80% RH on that surface. And then this number over here, this 0.24, which you can only use for operable door sills if you're trying to certify, is 0.24, I'm sorry. And that 0.24 is where you get liquid water on the surface. You get 100% RH, right? You actually get moisture forming, you can see drops, right? And they allow that for operable door sills and occasionally operable window sills, not usually, but once in a while, if it's a really good reason for it, is because those things they get dirty. So if you get mold buildup over, let's say, several years, it just gets cleaned off. And also you have additional ventilation. And typically door sills are also surfaces that are difficult for mold to grow on because they're made up of aluminum or glass or UPVC. So that's why they allow this easier criteria. The other place that criteria is often applied is interlockers on sliding doors because it's really hard to get high fRSIs on those. Okay, so what I did is I went and plotted across all the climate zones, and I did this just using a variance file, like we'll talk about next week in the advanced PHP class, for all the climate zones, and tried to look at how the ventilation rate, interior temperature, and fRSI interacted to produce what the requirement should be, and quickly realized, actually not very quickly, I'm a bit embarrassed, but eventually realized, to be honest, that if you took the ventilation rate per person, because the moisture generation rate in PHPP is a function of the occupancy, if you divide the ventilation rate by the persons, then you can plot everything just on a simple graph, right? So in this graph, on the x-axis is the ventilation rate per person in liters per second, which is what we use in the building code in New Zealand. And then on the y-axis, the fRSI requirements. And what you'll notice for the blue line is Auckland, the orange line is Wellington, and the gray line is Queenstown. I should use Christchurch, but anyways. So what you'll see is in every case for all ventilation rates, the fRSI requirement's more difficult in Auckland. In other words, you need a better envelope in Auckland than you do in Queenstown, right? And the reason being is that in Queenstown, the air is actually drier because it's actually cold outside in the winter. And so when you bring that piece of air in Queenstown inside, you heat it up to 20 degrees centigrade, it's got quite a bit of drying potential. So for the same ventilation rate, you can have a worse enclosure, if you want to call it that, right? Now, the minimum ventilation rate, 30 cubic meters per hour per person, which is what you're used to seeing in PHP. Nobody ever designs a passive house to that unless they're doing social housing. But if you did do a social housing project for passive house planning package, you'd be right at that red circle down at the bottom of those lines, like the lowest point you can do. If you do code minimum, which is 7.5 liters a second per person, which is what you typically design social housing projects to in New Zealand, you're at this line. And if you notice, Auckland's like 0.75, which is worse than 0.55. Actually, I shouldn't say it's worse, it's harder. It requires better windows and better details and stuff, right? It's more difficult. So, and then the reality is the typical passive house, the ventilation rate's more like 10 to 14 liters a second, because we tend to design a 150 square meter house with 3 people in it in reality. So typically the fRSI. So what this means overall for passive house designers is that throughout most of the country, especially south of Auckland, you can actually use poorer quality assemblies than you think you can and still meet the fRSI requirement. All right. It doesn't mean, so that means also that a window manufacturer that makes a window that does meet the passive house requirements in Auckland, don't really like to, but I'll mention a sponsor in this case. So APL's Centrifix 56 Passive, for example, which just hits 0.55 and was designed to just hit 0.55 to meet the passive house standard in Auckland when we had that cool colored picture, actually needs a bit more. You can crank the ventilation rate up to where you'd be in a typical passive house and make it work at 0.55, right? So if you're at, let's say, 12 liters a second, that's 0.55. So it works in Auckland, but that means that same window could be used in Queenstown. You may need to use a better profile for energy efficiency because the frames are still not very good thermally. Fair enough. But it means that you could use a single profile, a single thermal quality throughout the country. You just have to hit the energy target, right? So you could use those windows in Queenstown. You just need to compensate with insulation elsewhere in the building. A place where it might be good as a big multifamily or hotel or something, right? So this same graph, I want to talk about heating set point because it's really important. So if you drop the set point inside, this is just for Auckland. If you take Auckland with a 20-degree set point inside and you drop the interior temperature to 18 degrees or 16 degrees, what you find is that you basically can't get anything that works in Auckland. Everything molds if you're going to run your building at 16 degrees centigrade in Auckland. And the reason being is that when you take the outside air in Auckland in the coldest month and you bring it inside, it's got no drying potential. And this is why you've got students in student flats when they're like, I leave the windows completely open all winter and sleep under like 8 duvets and my house is still moldy. It's because they're not heating your house, right? It doesn't make them bad people, even if they have funny haircuts, my son. But it does mean that, that's the reason why their student flat is molding. It's because they're not heating it. Okay, so across the climate zones, I made this so you couldn't read numbers on purpose. In the paper, in the online slides, which will be online someday, you can see the numbers. But basically, as you drop the temperature inside the building, you drop the part of the buildings where you can actually get the building to work for reasonable ventilation rates gets harder and harder. And you start having to have like 90 liters a second of ventilation. 15 liters a second of ventilation to make it work. And quickly, it doesn't matter how high you ventilate, you can't get the building to work. Okay, so what's this mean for building code? So I want to talk about the building code, not the acceptable solutions. So I want to try to strike at the root, not the leaves. So there's all these interrelated bits of the building code, durability, internal moisture, ventilation, all this stuff. And I think that if we're going to try to get changes in the building code, we shouldn't look at changing the acceptable solutions the way we did in this last upgrade. As difficult as it's been, we should look at changing the code itself in legislation. And I've taken my cut at what I think I would do after having done this work, mostly focusing on interior moisture because that's the main health issue. So in B2, for example, I would put a new clause in up at the code level, right? Not down in the acceptable solutions that says that the assemblies need to meet ASHRAE 160, which is being used in Australia, by the way. It has to meet the mold index throughout the assembly. So you can't mold inside the walls, at least not heaps. Because 3 means you still have some mold in there, right? It just means it's not visible. For internal moisture, I changed from this clause where they've got like an adequate combination of stuff to make it healthy to a combination of thermal resistance that says we'll keep the RH in the building below 80% for any long period of time. All right. Surface RH, I'm sorry, the RH on the surface of the building. And then for G4 for ventilation, I just require ventilation to keep the CO2 level below 1200 for any 1 hour period. The acceptable solutions will then go ahead and tell you how you can do those things with a deemed to satisfy conclusion. But if you don't have the right targets at the top, you don't end up with the right acceptable solutions. You end up with the situation we have now where the acceptable solutions we know don't work in a lot of cases. For interior environment, I would just go ahead and aim what we want, which is, you have provisions in a building to maintain the internal temperature at 20 degrees centigrade while doing the other stuff we talked about. And for efficiency, I want to just bite the bullet and suggest we put a social justice metric in there that basically you can condition space to meet that 20 degrees C while not causing fuel poverty for new buildings. So they're not super difficult, and you can go ahead and go through these later at your leisure. But I think if we move our focus from acceptable solution things, we're looking at our values and edge insulation requirements and stuff, and step back up to what we want in the building at a top level, it's going to be more difficult because we can't just influence one government agency. You've got to get Parliament to change stuff. But it is a much more effective way to focus our attention, in my opinion. I'd enjoy some Twitter. I don't use Twitter, sorry. I do use LinkedIn. So you could smack talk about any of these and say how horrible they are or how good they are, or I should do something else on LinkedIn and I'll answer, maybe. But sorry, if you want to Twitter, you'll have to talk to Elron. Sorry, you can pass it on. In summary, this fRSI limit in PHP 10 allows a lot more options and allows manufacturers to now kind of more confidently design windows and other assemblies to meet across the New Zealand climate zones. And the great news is once you assume a reasonable ventilation rate in Auckland, if you've met the fRSI requirement in Auckland, you can then move it south. Looking across New Zealand, in the New Zealand Building Code, I think we underventilate in higher density housing. And the problem, that means that in social housing, a lot of times with code ventilation levels for the acceptable solution, if you just meet those, you're probably creating an environment where the occupants are going to get mold. Even if they behave well, they're going to have to behave extraordinarily well, like be a bit crazy about it to not get mold in their houses. Because they've got high moisture loads, they don't have mechanical ventilation, continuous mechanical ventilation. So even if they heat, they're going to have issues. Underheating results in conditions where you basically just can't make the building work. Doesn't matter who you are, unless you just don't occupy them. That works. And I think we should change the performance criteria in the New Zealand Building Code. That's where I'd like to see us focus our energy as a group.